Okay, so we have seen previously that when doing elimination, you would use operations like this one to produce zeros in the entry ij, right? And this here is the multiplier. And we've seen that you could do this by pre-multiplication of an elimination matrix eij. It's a matrix where you have ones on the diagonal, zeros everywhere else except in entry Lij, where you have to put minus the multiplier. Okay, so minus Lij. This elementary elimination that you've done using this operation, you could undo it by using this operation over here. Okay, so you're going to create the original element that you had in entry ij. Okay, so this operation, you can see it as the reverse, and associated with that is also a matrix. Okay, but since it's going to undo what you have done before, well, this matrix will be eij inverse. Okay, and this matrix will again be a matrix that you can construct from an identity matrix, and instead of putting minus the multiplier over here, well, you have to put Lij, so the multiplier, in entry ij. Well, we have used Gaussian elimination to produce an upper triangular matrix. Okay, and this upper triangular matrix, we'll call it U. Well, Gaussian elimination is at the basis of a decomposition of a matrix A, which we call the LU decomposition. Okay, so we assume here that there are no row exchanges involved. Okay, we'll see later what happens if you need row exchanges. Well, we have constructed U using Gaussian elimination, and we have seen that you can see this as taking your matrix A and pre-multiply by the product of all elimination matrices, right? So you pre-multiply A by the matrix E, which is the product of the elimination matrices, to produce an upper triangular matrix. Okay, so if you pre-multiply this equation by E minus 1, well, you have here the identity matrix. Okay, so you end up with this equation here, and the inverse of this matrix E, which is the product of the elimination matrices, is a matrix L, and we'll see that this matrix is lower triangular. Okay, and that is very easy to construct from the multipliers. Well, let's have a look at this in a 3x3 case. So you have your matrix A, and you want to make it upper triangular by doing elimination. So you want to produce zeros in the entries 2, 1, 3, 1, and 3, 2. And these are the associated elimination matrices, and the global product is E, right? So A is E minus 1 U. This one we'll call L. Okay, E minus 1, you will find it over here. Okay, so this is indeed correct, because you know that matrix A times B inverse is B inverse A inverse. Okay, so we have to reverse the order. This is indeed the case over here. So the inverse of E is constructed from the reverse product of the inverse of the elimination matrices. Let's take one of these inverses of the elimination matrix, and you know that you can construct it from the identity matrix, and in N3ij you have to put the multiplier. Okay, so here Lij, right? So indeed this matrix is lower triangular, and L, which is also equal to E minus 1, is the product of lower triangular matrices. And you can show, and maybe you should do this as an exercise, that the product of lower triangular matrices is itself lower triangular. So L is lower triangular. Okay, remember that U was upper triangular, and the entries of L are the multipliers Lij, and we'll show this next. Okay, so this is the exercise that we've been doing before. We want to bring A to an upper triangular form, and you see it's upper triangular. So in first instance we make zeros below the pivot, so the multipliers are the entries divided by the pivot. So this gives me a multiplier 2, 4 divided by 2, and a multiplier minus 1, minus 2 over 2. You do these two operations and you end up with this intermediate matrix. You have now a new pivot, okay, and we construct a 0 below the pivot using this multiplier over here. It's the entry divided by the pivot, okay, and you end up with this upper triangular form. So the elimination matrix 2, 1 that will produce a 0 over here is the identity matrix, where you put minus the multiplier over here. Okay, so we can do the same thing for E31 identity matrix, where we take the opposite of the multiplier, so we'll have a 1 over here, and also matrix E32 identity matrix, we are creating a 0 over here, so we take minus the multiplier, so it's a minus 1. We can also construct the inverses. Okay, so it's identity matrix. Okay, and we do the reverse operation, so we have to take minus the multiplier. So, sorry, not minus the multiplier, the multiplier. So 2. So here we take the multiplier, and we'll end up with this matrix over here with a minus 1, okay, and here we'll obtain a matrix with a 1 over here, because that's the multiplier that you see over here. Okay, so it's quite easy to construct the elimination matrices and the inverse of these elimination matrices. Okay, so here are the elimination matrices that we had computed in the previous slide with their inverses. Okay, so if the elimination matrices are combined, you have the global elimination matrix. So E times A is the upper triangular matrix U, and now if you pre-multiply by E minus 1, you can write A as E minus 1 times U. Okay, this is U, and we've shown that this matrix, which we call L here, is lower triangular. So E minus 1 is the product in reverse order of the inverses of the elimination matrices. So the question is, how will this matrix look like? And this is answered in the 2 next slides. Well, let us first maybe have a look at the product of the elimination matrices in the order in which they are applied. So E2 1, E3 1, and E3 2. This is minus the multiplier here, minus the multiplier, and minus the multiplier. Well, if you do the product of these 3 matrices, well, you can kind of see that you cannot easily construct E using the multiplier just because of this element over here. Okay, so E21, you can read this from this line, okay, implements that the new row 2 is the previous one minus 2 times row 1. Okay, E31, third line, you can see this. The new row 3 is the old row 3 plus row 1. This is what you see in this line over here. And E32 implements, well, the new row 3 is the old one, the one that had been computed previously, minus the new row 2 that has been computed over here. So if you inject this one over here and this one over here and you do the calculations, you see that the final row 3 here is obtained like this from the original matrix. Okay, so you see that there is a mixing that is occurring here, and you cannot construct E from the multipliers. It's okay for this and this element, but in this case here not for this element. Well, let us now look at the matrix E minus 1. Okay, and this is this matrix L that is of interest in the LU decomposition over here. So okay, so E minus 1, because of the properties AB inverse is equal to B inverse A inverse, well, you can be written like this. So it's the inverse of the elimination matrices in reverse order. Okay, so this is E32 minus 1, E31 minus 1, and E21 minus 1. So this one, you can see it over here. It implements this operation over here, right? This matrix here implements this operation over here. Okay, it starts from the row 3 that was obtained over here, and this one over here, okay, implements, you can see this from this row over here, this operation. If you bring this thing here inside of here, you obtain the 2 following equations. Okay, and what you see is that row 3 is minus row 1 plus row 2 plus row 3, and here E minus 1 is equal to L can actually very easily be constructed from the multipliers. There is no mixing over here. So to construct L, it's very easy. You start from an identity matrix and you place the multipliers at the right spot, and you have your L matrix. Well, let us take our example that we had considered previously. Okay, so we had shown that using row operations you could obtain the matrix U, which is upper triangular, and on the diagonal you have the pivots, right? Remember that we were using these multipliers. Okay, and the multiplier is simply obtained by considering the element that you want to make 0, okay, divided by the corresponding pivot. And we have just shown that in order to construct L, this was U, well, you simply had to take a identity matrix and put the multipliers at the right spot, and at the right spot means at the spot where they are creating a zero. This multiplier is creating a zero over here, so we simply put it over here. This one is creating a zero over here, so we put it over here. And this one is creating a zero over here, so we put it over here. And we have our LU decomposition. Okay, I want to stress the fact that my definition of a multiplier is that you have a minus sign here. So for this LU decomposition, and in order to use this very systematic way of constructing L, you have to work in the same way, in the sense that you're always working with a row minus another row, and that you don't have a plus over here. Well, what you have just done in this example is to decompose A into L times U. Sometimes you would like to go a little bit further, and we would like to write A is equal to L du. Okay, remember that L on the diagonal has one element. Well, you could do something similar for the upper triangular matrix, so that you have ones on the diagonals and the pivots sorry, on the diagonal matrix. In order to do that, you can rewrite U in the following way. So we put the pivots on the diagonal, so this will be my D matrix. And what you have to do, because you put, these are all zeros over here, because I said it's a diagonal matrix, because you put the 2 up front in the diagonal matrix, you need to divide this whole row by 2. So it becomes 1, 2, minus 1. Here it's a 1, so no problem, you can recopy this and this. And here you put the 4 in here, so this will become 0, 0, 1. And this is an LDU decomposition of the matrix A. So this is what I've shown in the previous slide, and again we assume that there are no row exchanges. In the slides that will follow, we'll consider row exchanges. So the LDU decomposition, okay, U is now upper triangular, and on the diagonal you have ones. In the diagonal matrix you have the pivots, okay, and in the lower triangular matrix, well, you have the multipliers that are at the spot where they create a 0 in the upper triangular matrix. Well, remember that we had considered permutation matrices, where we interchange rows of the identity matrix. Okay, of course there is the obvious identity matrix where you leave everything as is, and you have, in this case, because we use here 3 by 3 permutation matrices, 3 types of elementary permutations where you interchange 2 rows. For instance, here you interchange row 1 and 2, here 3 and 2, and there 3 and 1. Of course, you can do more than one permutation, okay, and then you can end up with non-elementary permutation matrices, and here we have the 2 examples that come on top of what we had already seen for a 3 by 3 matrix. In general, if the matrices are n by n, there are n factorial permutation matrices. If n is equals to 3, of course the factorial of 3 is indeed 6. These are the 6 cases that you see on the slide. I've been talking about permutation of rows, but of course you can do similar things with permutations of columns, but there you have to consider post multiplications. Well, non-elementary permutations, and you have 2 examples over here, are the product of elementary permutation matrices. So let us take a matrix P, which is the product of Q permutation matrices. Okay, so these PI here are elementary permutation matrices. So we know that PI is equal to its transpose, and it's also equal to its inverse. Okay, so if we write P inverse, remember that AB minus 1 is B minus 1 A minus 1. I've been using this several times, so by now you should know it. Well, you can obtain using this you can obtain the expression of P minus 1, which is this one over here. Okay, so we know by these properties here that the inverses are equal to the matrix itself. So the inverse is equal to this thing here. But since the order of matrices is important, in general AB is different from BA. This might be allowable and this might not be allowable. But even if it's allowable, in general it's different. So we have that the inverse of P is different from P. Okay? But this one here is also equal to its transpose. Okay, so we can write the transpose, and this indeed is equal to the transpose of P. So we have that P minus 1, the inverse of P, is equal to its transpose. Okay, and this is a property of a general permutation matrix. Okay, general in the sense that it's the product of several elementary permutation matrices, and we'll see later on in the course that this is a special type of matrix which we call an orthogonal matrix. When you do Gaussian elimination, sometimes you can have a temporary failure, and the pivot is 0, and you have to do row exchanges to solve the problem. Okay, and in this case it will not be possible to write a decomposition of A in terms of L and U. Okay, this is because of one or more row exchanges. So what you can write instead is something that is close. P, which stands for the permutations, the one or more permutations that you have done, times A is equal to LU. And you can see this as if you're doing the permutations up front, and you take the resulting matrix and you do an LU decomposition. For your information, packages like MATLAB, they use row exchanges to bring the largest pivot in place and have less numerical problems. Okay, this is called Gaussian elimination with pivoting, and this occurs when you solve the system AX equals to B using the MATLAB command A/B. So what is implemented goes a bit further to what we have seen here in the course. It's Gaussian elimination with pivoting. So here's an example of that. In this matrix, when you attempt to do the LU decomposition, you have a problem up front, right? Because you cannot take this one here as a pivot. Okay, so you have to interchange the rows to obtain this matrix over here. Okay, so now this is your pivot. You have created a 0 over here, and you need to create one over here. So the multiplier is the entry divided by 1, this one here. You do the operation, you create a 0. You have a new pivot, you need to create a 0 below. Multiplier is entry divided by pivot, so you have a 3 over here. You do this operation and you end up with the matrix U. Okay, so this is also equal to this matrix over here. The multipliers are over here, so this is L, okay, but this is the LU decomposition of this matrix over here. In order to obtain this matrix, okay, from A, you need to use a permutation matrix. So you have PA is equal to LU. Okay, and here we have exchanged row 1 and 2. So you start from the identity matrix and you exchange these rows, and this is indeed the permutation matrix that you obtain. Well, you can ask yourself the question, what is the use of doing this kind of decomposition? So in general, in lots of cases, P will simply be the identity matrix, but I have taken here the general case. Well, this can be used in solving linear matrix equations or systems of equation of this type, where A is always the same and B is always different. Okay, so this happens when you do calibration. So you're always measuring the same reference, but the result is always different, okay, because you make errors, okay, using a scanner or something like that. Then you end up with a system AX equals B. Okay, well, what we can do is use the decomposition over here. Okay, so if we pre-multiply this equation, we have PAX is equal to PB, but we've just seen that this thing here is PA. Okay, so in order to solve this equation and to solve it in an efficient way, you can compute upfront this decomposition. So you know L and you know U. You have to do the work one time, and then what you do is simply say Ly is equal to PB. Okay, and L is lower triangular. Okay, so you have a Ly is equal to a vector. Okay, and this is easy to solve if you're using forward substitution. You're starting from this equation here, and you simply have to divide what you see over here by the element over there, and then you continue in this direction using forward substitution. Okay, so now you have obtained, since you have solved this equation here, this is the y that you have over here. Okay, so you know now that since you have y, you can solve the second system. Ux is equal to y. So this was my L over here, and now we have a matrix that is upper triangular. Okay, so this was my PB over here. This is U. This is the X I'm looking for. Okay, and here you put the Y that you have obtained in the first step, and this is an upper triangular matrix, so you start from the bottom and you do backward substitution. Okay, and you can show that if you do that and you have computed upfront L and U, that is far more efficient from a computational point of view, but also from a numerical point of view, than to compute each time A/B. Okay, so this thing here is faster and it's numerically more reliable. A matrix is said to be symmetric if it is equal to its transpose. So A is symmetric if A transpose A is equal to itself. So let's take an example, and for instance this matrix here 1 2 4 4 is symmetric because it's equal to its transpose. Okay, Aij is equal to Aji. It is quite easy to construct symmetric matrices from any rectangular matrix, and this one has m rows and n columns. So R transpose, well, this is m times n, and this one is n times m. So the resulting matrix is m times m. So it is square. Okay, and you could also do this thing here. This is n times m and transpose, and this is m times n. So this one is also square, but it is n times n. Okay, so first thing that you can already see is that this matrix here is square and this one is square. They are not the same. It's obvious because they don't have the same dimension. So we can, for instance, see that this one is here indeed symmetric. If it is symmetric, then by taking its transpose you should obtain the same matrix. So let's take this matrix here and take its transpose. Don't forget that A, B transpose is equal to B transpose, A transpose. Okay, so you take the transpose of R, well, this is R, times the transpose of R. So we end up with this. Okay, so we see that this matrix is indeed symmetric because it is equal to its transpose. You can do the same for this one over here and show that it is also symmetric. Well, when a matrix A is symmetric, you can do its LU decomposition, but the fact that it is symmetric will be hidden into this LU decomposition. So you should actually then use an LDU decomposition. Okay, and this is the matrix A that we had been using before to compute the LDU decomposition. Okay, it turns out that this matrix is equal to a transpose, so it is symmetric. Okay, and indeed what we see is that we do this kind of decomposition LDU, we see here that the U that we have over here is actually equal to L transpose. Okay, so if the matrix is symmetric, you can go a bit further and obtain an LDL transpose decomposition.